I maybe talk a little bit fast. So hello, I'm Stan, and I'm a PhD student under testing. Is it okay? Okay, so I'm under the supervision of Prof. Wang, and today this lecture will be about. Yes, put it here. Okay, thanks. Yeah, I get it. Okay. So today this lecture will be about the project I've been working on, that is constrained automatic music generation and manipulation for rhythmic auditory stimulation. So before music, let's equip ourselves with some knowledge about Parkinson's disease. Now there are over 5.8 million people with Parkinson's disease over the world, and this number is still increasing and will double up to 8.7 million by 2030 from 4.6 reported in 2005. And people with Parkinson's disease often experience disorientation with tremors, unstable postures, and slowness of movement, resulting in an inconstant gait when walking. And now there is no cure for Parkinson's disease. That is very sad, but fortunately, rhythmic auditory stimulation, RAS for short, is shown to be very helpful to improve the gait of the people with Parkinson's disease. So in RAS, a patient will walk with a rhythmic stimuli. Usually it's a metronome. And the rhythm of the stimuli will serve as an external cue to compensate the dysfunctional internal cue of the patient's brain.
Just a quick comment. Everybody has seen this video already, right? So you can skip this.
Okay.
Yeah.
So so the video is to show that RAS is very effective. And the traditional RAS use metronome as a stimuli. So imagine if you're a person with Parkinson's disease, are you willing to listen to something like this for 30 minutes every day? So it sounds like this. I guess nobody wants to, so because it's so boring. So metronome may not be the most motivational stimuli for a lifelong rehabilitation. And that's why music therapists try to combine music with metronome to make this progress more enjoyable. Sorry. So now it sounds much better. But the current RAS with music is not accessible for most of the patients. And the reasons are as follows. Firstly, since no music is suitable and preferable for all the people with Parkinson's disease, so it requires a professional music therapist to produce or select a personalized music playlist for each patient. And this is not usually practicable because it costs a lot of time and money. And secondly, it is difficult to modify, which means now the current RAS use music in raw audio format, so it is hard to change the music's tempos and beat strengths in real time. And this to features. And thirdly, it is hard to regenerate a new playlist, which means after a playlist is generated, if you want to regenerate a new playlist, it requires a music therapist to do it again. So a patient may get bored with the current playlist and give up halfway. So our goal is to design accessible and cost-effective RAS. The patient will wear smart sensors which will detect their gait and analyze their gait, and the result of the gait analysis will be sent to the music generation system to generate personalized music for each patient. So my research is focusing on automatic music generation for RAS. And basically, the generated music have some clinical requirements. The tempo should match the gait tempo of a patient, and the time signature should be 2/4 or 4/4. And the beat strength of the generated music should be strong enough to serve as the external cue. And also we want to satisfy a patient music preference by imitating some sit sounds, which I will talk about later. If you have ever joined a music band, you will be familiar with lead sheet music. A lead sheet includes all the necessary components of a piece of music. It has drums, chord progression, bass, and melody. So lead sheet will also be the output format of our music generation system. And our system applies a feasible workflow for human music composition. So first it will choose a tempo, and then it will generate the structure of the music, which means how many phrases are in a song and how many bars are in each phrase. And then it will generate drums. And next step, chord progression, and then bass. Finally, generate the melody. And now I will give you a demo. So these 4 parts will come in one by one. Then you can get a basic idea how these components function in a song. So at first, there will be only drum channels. And now the chord comes in. And then the bass. And finally the melody. Okay, after we listen to this song, we may have an intuition of the contributions that different factors in the song makes to the music similarity. So how can you recognize or distinguish a song? So the first, the component matters the most is the melody, then followed by the chord, bass, and drums. So if I hum like dun 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 dun, and you will immediately recognize that it's just the song I heard, right? And if you have ever listened to some remix versions of a song, there will be some changes in chord progression, bass, and drums. But as long as the melody keeps the same, you can always recognize that it is the same song. So let's think about another question. So if you want to generate a song for a specific applications like RAS, what do we care? What we want the generated music have? Okay, the fundamental is domain-specific requirement. So the generated music should satisfy the requirements of an application. For RAS, it's tempo, time signature, and beat strings. And a higher level, it should be musicality. So the generated music should be in line with music theories to make it sound decent. And a higher level is music preference. So the generated music should match the user's music preference. Which means if you generate music for specific applications, we want creatively to satisfy the music preference and enhance the efficiency better and better during the iterations. Okay, so if you can still remember the contributing factors to music similarities, if we want our generated music to have all the features, we may want the generated melody to have all the features, and the chord may have 3 or 4 of these features, and the bass may 2 or 3, then drums 1 or 2. So how can we guarantee the generated music have the features? For domain-specific requirements and musicalities, we can use a rule-based method to guarantee these two. And then for music preference, we can use a music preference model, the CSON. I will talk about this later. So we can satisfy user music preference by imitating the CSON that they like. And for refinements, we can use reinforcement learning. existing music generation system, they can be categorized into 4 classes: rule-based, statistical-based, evolutionary, and artificial neural net-based. So now we know what we want for the generated music. If we want to guarantee the generated music has the features, what properties should the music generation system have to guarantee the features? So first, it should support including a seed-song. This is to guarantee the music preference. And it should support adding constraints. This is to guarantee the domain-specific requirements and musicality. And low time complexity. Yes, we don't want the users to get their musics waiting too long. And also we want the reinforcement learning part to get very quick response to converge fast enough. And also the long-term structures. This is also to guarantee the musicality of the music. But none of the models here have all the properties at the same time. And now there are a lot of studies on using neural network to generate music. But it would be challenging for neural network-based models to generate useful musics for our target application, RAS. Because we are still lacks a very suitable representations of music in neural networks. So it is hard to add any explainable constraints to the neural network. And also it takes a long time to train the model. And it is hard to collect a data set of the songs that the users like. And also, even we use LSTM or attention mechanism in the neural network, a song usually lasts for like 3 minutes or even longer. So now the long-term structures in the neural network may be not long enough to generate music for RAS. So we have explored an alternative approach for SAT, that is a rule-based model plus a statistical model, which provide following advantages. First, it can include seed-songs. Yes, we can learn the tradition of the notes of the seed-song, and we can add constraints by the rule-based model. And both rule-based model and statistical model are fast. So we assume a combination of them is fast too. And for the long-term structures, we can copy or imitate the structures of a seed-song to guarantee that. And that's why we choose our baseline model. It is a pop music generation framework. So besides the general advantages of a rule-based model and statistical model, this framework is also highly modular. So it means we can easily modify or substitute some parts. For example, we can modify the drum generation part of the framework, and we can substitute the melody generation of the framework. So that's why we choose the baseline model. The seed-song. So the seed-song is a MIDI file. It is selected by a patient, and thus we assume it reflects their music preference. And then we will feed a seed-song generation system and try to imitate the style of the seed-song. And before a seed-song can be used in our system, we have to do some preprocessing. So the seed-song may not have a time signature of 4/4, and the key signature may not be C major. So we develop some tools to transfer the time signature and key signature to 4/4 and C major. And also we need to transcribe the MIDI files into a machine readable data. And now we're doing this by hand. Okay, let's see how the system generates music. So if you can remember the workflow, the first step will be a tempo. So the system will select the tempo, and for RAS, it's just select the tempo matching the patient's gait. And this is to guarantee the domain-specific requirements. And now we have the tempo, then the system will generate structures. So it will first try to copy the structures of the seed song. And the structure of the seed song may look like this. A letter here, A, B, C, D here, represents a different kind of phrase. And the numbers here means how many bars are in this kind of phrase. Here, the seed song has 36 bars. And if the target length of the generated song is the same as the seed song, the structures of the seed song. And if it is longer than the seed songs, we will insert some new phrases or the repeated phrases of the previous one, and we may rearrange some of the phrase. For example, here we will move the non-4 bars phrase here to the beginning as an intro part. So now we have already generated tempo and structures. Then the system will generate drums. 1 bar in the system is quantized into 16 time slots. And the numbers here means that the probabilities that a drum occurs at this time slot. So for RAS, due to the domain-specific requirements, the drum is quite simple. The drum just occurs at the first time slot of each bar. So in RAS, the drums just sound like this. It's very similar to the metronome. Okay, and if we are generating a song for some other applications which do not have this requirement, the drums may sound more colorful, like this. Okay, so now we have tempo, structures, and drums. Then we will generate chord progressions. And the basic idea of chord progression generation is based on Markov model. So it always starts from chord 1, then it will generate the following chords one by one according to a predefined transition matrix. This is to guarantee the musicality, and it is defined in the baseline model. But besides musicality, we also want to satisfy the music preference of the users. So we want to change it from predefined transition matrix to imitating the chord progression of the seed song. So let's think about a question. What makes a chord progression of a song different from other songs? And the answer may be the unique chord sequences. Unique chord sequences are the chord sequences in a song that appears very rarely in other songs. So our goal is to detect the unique chord sequences in the seed song and use them to generate the chord progression of the generated songs. So how do we detect the unique chord sequences in the seed song? We have a chord sequences dataset, and we do 234 gram chord sequences statistics based on the dataset. And we set a threshold, so the chord sequences occurs less than the threshold will be tagged as unique. Then we go to the seed songs. We also scan the chord sequences. For the 2 gram chord sequences in a seed song, they will form another transition matrix. So this transition matrix is produced by the 2 gram chord sequences in a seed song. And for the 3 gram and 4 gram chord progressions, we will match them with the statistics of the dataset. If it is tagged as a unique, we will add them to the transition matrix and normalize the probabilities. So now we got a transition matrix produced by in a irregular shape. So we have a transition matrix that is manually predefined, PR1, and we have a transition matrix produced by the seed song, PR2, and we will blend them together with the parameter alpha. So alpha determines how much we depend on the music theory rules and how much we depend on the seed song. Okay, and we also want the generated chord ending with cadences. Have you ever heard cadences? So cadences is like the punctuations in a language. It allows us to predict if now it is the end of a phrase or not. So, for example, let's listen to this demo first. Okay, so in this phrase, there are two cadences. Here, the chord 4/5 forms half cadences. So when music goes at here, you have a feeling that the music is going to continue and it is not the end of the phrase. And here, the chord 5 to 1 forms a perfect authentic cadence. So here, you may have the feeling that this is the end of the phrase. So let's have a listen again. You can. Oh, sorry. So we want the generated chord progression conforms to the same cadences like the sixth song. So that's how we do this. We enumerate all the chord sequences ending with a cadence, and we call them paths. And then we will assign each path a score, and it is calculated like this. This is the product of the transition probabilities along the path, and the score is length minus 1 root of the product. So now we have a list of paths and their corresponding scores. And here is how the the system generates chord progressions. It starts from chord 1, then it will use a Markov model, the blending transition matrix, to generate the next and next chord. And at each step, it has a probability to trigger this ending with cadences algorithm. So if the algorithm is triggered, like here, it will selectively choose a path from the list and fill all the remaining chords, and then move to the next phrase. So now we have already generated our chord progression. Then follow the workflows where we generate the bass. Is represented as numbers. So 0 to 28 means the relative pitches of the bass note, and -1 means holding the previous note, and -2 means silence. So the bass here, you have 0, 0, 4, so it sounds like this. Okay, one more time. Okay, so the basic idea of bass generation is we have rhythmic patterns and we have pitch patterns. So the rhythmic patterns is the locations where the bass is occurred and the duration of a bass note. The bass here is an example, and the rhythmic pattern of the bass here is like the cross here, cross, cross, and cross, and dash, dash, dash. So it has nothing to do with pitch. It's just the time slot that a new bass note is turned on. And then in each phrase, we will use sliding windows to match the rhythmic patterns and count the frequencies that all possible, count the occurrence of all possible rhythmic patterns and find the most common one as the patterns of the generated bass. And here is an example. Okay, so for the first phrase here, the rhythmic pattern is very obvious. It's just like bam, bam, bam. Okay, so now we have our rhythmic patterns, but we still need some pitches. So then we need to assign pitches to every bass note of the rhythmic patterns. And this is the pitch patterns is a combination of the music theory rules and the statistical features of the bass of the seed song. So it is based on penalty functions. For each possible pitches, it will calculate these penalties based on some music theory rules, which is defined in the baseline model, and also the statistical features of the bass in the seed song. Basically, it includes the note transitions and the chord-based pairs of the bass of the seed song. Okay, and finally is the melody generation. Melody generation is very similar. It also has the same representations, and it also have the rhythmic patterns and pitch patterns. So the rhythmic patterns of melodies is a little different from bass. Since we want to imitate the seed song, you remember the contribution to the similar music similarity, right? So here we, for some of the phrases in the melody, it can copy the melody rhythm from the seed song melody, and for other phrases, it may be freely compose the new rhythmic patterns according to music theory rules. And here there is a parameter gamma to control how many phrases are just copying the rhythm of the seed song and how many of them are freely composed. And now we got our rhythmic patterns of melody, and to assign them some pitches. And yes, we also have some rules that is predefined in the baseline model, and that is part of the penalty functions. And we also use statistical features of seed songs as some other penalty functions. And it cares about the pitch frequencies, the pitch transitions of the melody, I mean 2 consecutive pitches, and the chord pitch pairs of the melody and chord. So now we have the penalty functions defined according to music theory rules, and we have the statistical features of the seed song melody, and we use the parameter beta to control how much it depends on the music theory and how much it depends on the statistic features of the seed song. And another way to imitate the melody of the seed song is like using the contour. So for each note of the generated song, we will also give it a penalty when the contour of the generated melody does not match the seed song. So we have 2 modes, distance mode and interval modes. And these 2 modes are both used to calculate the penalty of the contour. In distance mode, the penalty of a note is the difference between the note in the generated melody and the corresponding note of the seed song melody. And in interval mode, the penalty of a note is the difference between 2 consecutive notes in the generated melody and subtract the difference between 2 consecutive notes in the seed song melody. And that's how we calculate the penalties of the contour similarity. And you may notice that we have a theta here. The theta is like the weight of the contour penalty. So it means how much a user cares about contour similarities over others, like the statistical features and the musical theory rules. So that's it's like a bias parameters along all the penalty functions. And here is an example of the contour similarities. And now, and this is the melody of the sixth song. So the generated melody here sounds very similar to the sixth song because it's just a transfer melody. And in this case, our interval mode will be more reasonable because in this case, the melody mode, the interval mode will give it 0 penalties. And now let's listen to another example. So these generated melodies not sound so similar to the sixth song. So in this case, if we use interval mode, the penalty is still very low and it's not so reasonable. So in this case, the distance mode will be more reasonable. So the tricky thing is when to use interval mode and when to use distance mode. And in our system, we use distance mode in some very key positions like the first note in each phrase or some downbeats. So this is to pull back the melodies back to the track of the sixth song. And in the other positions, we will use interval mode to allow the melody generation more creative. Okay, so if you can still remember, we have some parameters to control the similarities of the generated song. Alpha is this to control the contour similarities. It means how much we depend on the music theory rules and how much we depend on the transition matrix produced by the sixth song. And beta to control the melody statistical features. It is like the same with alpha. And we have theta to control the contour similarities. It determines the importance of the contour similarities. And we have gamma to control the rhythmic similarity of the melodies. It means how many phrases are copying from the sixth song and how much are newly generated. So if you set all the parameters to be 1.0, the generated song will be identical to the sixth song. And if you set all the parameters to be 0.0, is free composition, just follows music theory rules. So for our users, you can like generate very personalized music by adjust the parameters here. Okay, so if you can still remember the features of the generated song we care about, the domain specific requirement and the musicality, the music preference, and now we are going to refinement. Since it's a music generation system for a specific application RAS, so the patient will do rehabilitations in the mobile app, and after each training, it will he or she will give some feedbacks, and then the program will use reinforcement learning to learn models according to the feedbacks of the patient, and in the music adjust the parameters. So the generated music will like adaptively refine according to the feedbacks and regeneration music. Okay, that's the most exciting part, the demo. So the sixth song is Havana. So I guess all of you have listened to this song, right? And the parameters here are set as this. So the gamma here, the rhythmic similarity is said to be very high. So the generated song may have very similar rhythm of melodies like the sixth song. This is easier for us to compare. So let's have a listen to the sixth song first. Okay, and now the generated song. The drum here is for, the domain-specific requirement. And in the beginning, it sounds like the same with the sing song. Okay, so how do you think about this generated music? And there are some further very interesting research topics. And the first one is automatic MIDI content analysis. So if you can remember, we did some processing to transcribe the MIDI file into machine readable data. And now we'll do this by hand. So this is very slow, and it's limited the library of our stage songs. So if we can have a model to automatically recognize the MIDI channels, like telling you which one is a melody channel, which one is a chord channel, and so on, and automatically annotate the chord, and also partition the phrases. And this process can be done by machine, and it will enlarge our library of stage songs in a very large scale. And secondly, do we still have time?
Better wrap up quickly. So,
okay. Yeah, so this is there is a demo. It is also Havana, and it is subtly arranged by humans. So we may have a very quick lessons.
Okay.
Okay, I think that's enough. So compared with the stage song and generated song we just heard, this I think it sounds much better because it is an expressive performance. So now the generated music are mostly like the playing performance. You just play certain pitches at a certain time, and but in real music there are fading and fade out and some other spatial performance techniques for different instruments. So we may have a model to automatically detect the emotions of music. I think Dory is an expert, and program the instrument and use the correct performance techniques automatically. Then that will make the generated sounds much better. And I think that's all.
Okay.